electric field due to a line of charge. We now consider charge distributions that consist of a great many closely spaced point charges that are spread along a line, over a surface, or within a volume. Such distributions are said to be continuous rather than discrete. Since these distributions can enclose an enormous number of point charges, we find the electric field that they produce by means of calculus rather than by considering the point charges one by one. Electric field due to a line of charges. Now, here we have a uniformly distributed line, okay, which is a ring, it's a ring with radius r. We are asked to find an electric field at point P, which is on its central axis, distance z from the center of the ring. The radius of this ring is capital R. Okay. How do we find the electric field at point P on the central point? We divide this ring into a very small section we call the ds. ds carry charge dq. The E at P looks like a 2 point is the electric field produced by point charge ds is along this line. The ds equal to 1 over 4 pi epsilon dq over r squared, and this r squared equal to, in this rectangular, equal to z squared plus big R squared. And the dq equal to ds multiplied by the charge density rho. Okay. The rho equal to whole charge q divided by its length 2 pi r. Okay. Now, because of the symmetry situation, we take another section ds, same length in the another end of the diameter. Okay. And this charge will produce E at point P like this one. The magnitude dE must equal to this dE because of the symmetry reason. And we can find out, okay, these two, combine these two, only the Z component, the E component along the Z direction overlap. The perpendicular to the Z direction, they cancel out. So we take the charges in pair, many pairs. Each pair, their dE is along the Z direction. So finally we say each dE, its component along the Z direction makes final contribution. Okay? So we have the dEz, they make contribution, equal to dE cosine theta. And the cosine theta in this direction is equal to z over r. And r is equal to z squared plus big R squared. Okay, then finally we do the E equal to dz integration. Okay, dz equal to dE cosine theta. This is dE, this is cosine theta. Okay, we put it. dE equal to 1 over 4 pi epsilon 0 q lambda ds r squared. This is z. Cosine theta equal to, first z over r. Z over r equal to z squared over big R squared. Okay? And we do the integration wrong. Okay? Let me write it. This is z lambda. Okay? This is a square. This is 1. So the word 3 over 2, 3/4, 3/2. Okay? So we do the integration. It looks very complicated. Actually, it is not, because what we do the integration is along this one, the ds. And all these z are nothing to do with s. So we can rewrite this integration as, put this one inside, integration ds. And this integration diffraction equal to total length of this ring, 2 pi r. 2 pi r is the length multiplies density, you get the Q. So the E equal to ZQ over 4 pi Z squared R. Okay, we get the answer. Now, if the R is approach to 0, so this ring become the point charge. So this become the electric field, the point charge, like Coulomb's law. So with R equal to 0, Z squared, we get this cancel one Z, we get Q for pi Z squared. This is the electric field produced by point charge, right? Sample. Figure shows a plastic rod having a uniform distributed charge minus Q. Totally is minus Q. The rod has been bent in a 120-degree circular arc of radius r, small r. We place coordinates axis such that the axis of symmetry, this is x, of the rod line along the x-axis. So this is x-axis. Okay. The orange is at the center of a curvature P. Okay. In terms of Q and R, what is the electric field E due to the rod at point P? Now, we have a symmetry with respect to axis. So, if we take a very small section of charge here, ds, corresponds to d theta, then we can have another one by symmetry, okay? In this case, because the negative charge is towards the asymmetry, so we find only component along x direction makes final contribution. The E along y direction will cancel out with each other. We take pair, they always cancel out. So what conclusion is, the final E is along the x direction, right? Yeah. Okay, then we find the dE produced by this one, at this point, dq over 4 pi epsilon r squared. What is dq? dq is ds related, equal to lambda ds 4 pi r squared. Okay, what is lambda? Lambda equal to q, ds equal to r d theta. And so along x is dex equal to de cosine theta. Okay, and de is lambda ds 4 pi over 4 pi epsilon r squared cosine theta. Okay, and then we ds, what is ds? ds is r d theta. The r cancel out 1, we get the r d theta. Okay, and then we do the integration. This integration is very simple because cosine theta is sine theta. The r is constant, okay? And we're starting from minus 60 degree pi over 3 to positive pi over 3, okay? And this is a very simple integration. I'm going to do it, not do it. So we get equal to lambda over 4 pi epsilon 0 rho sine theta from minus pi over 3 to positive pi over 3. We get this number. And the lambda is q over the length. Q over what the length is about, this is 120, so it's about 1/3 of circumferences, okay? 2 pi r over 3, okay? We put the lambda inside this one, and we get E. It's by symmetry, only EX, okay? And we put this one lambda inside, we get this answer. This is a simple calculus. We can calculate, use the electric field P by uniform distributed charge. So the calculus. In this book, with the charge, we use the Q, symbol Q. The unit is coulomb. Linear charge density is Q over meter, lambda we use. Surface charge density, sigma, is coulomb over square meter. Volume charge density, rho, coulomb over meter cubic. A thin non-conducting rod of finite length carries a total charge Q, spreading uniformly along it. Show that E at point P on the perpendicular bisector, this is a bisect, half, bisect, in the figure is given by E equals Q over 2 pi epsilon 0 y. Y is the distance of P to the rod. This is a constant in this question. Okay. Let me see, we pick up very small, tiny dq. This is a dx, location at x. The center of this rod we take as the origin of the axis, okay? And then for this part of dx, very small section, with charge dq, the electric potential at P is equal to 1 over 4 pi epsilon 0 dq over r squared. This r is the distance P to this point in this question is equal to x squared plus y squared square root. Okay? And the dq is equal to lambda ds dx. Lambda is the charge density, linear charge density, okay, which is equal to Q over L. Okay. All right, so this is dE. And we will see that if we symmetry, we take another dx this relatively to this one. So you have dE along this direction. We can tell that the combination of these two dE must be along the y direction, right? By symmetry reason. So dEy is the final result, and the dEy equal to dE multiplied by cosine theta. And the cosine theta in this triangle is equal to y over square root x squared plus y squared. Okay. So cosine is y over x squared plus y squared. Okay. Then we know so dE, the total E must be integration of dEy equal to dE cosine theta. And dE is this one. Cosine is this one. We put them. So dE equal to 1 over 4 pi epsilon 0 lambda dx over x squared plus y squared. And cosine theta equal to y over square root x squared plus 3. And then we combine these two, we get it. Answer is y lambda 4 pi epsilon 0 x squared plus y squared to the power of 3 half dx. Okay. And I see this integration is not easier to do it. We check the integration table. Okay. And integration x is minus half L to positive half L. And we check the integration table, we find dx over x squared plus a squared to the power of 3 half is equal to x over a squared plus square root x squared plus a squared. So compared to this one, a is equal to y. So we put this one inside, we get it. The answer is just, the integration is from minus half L to half L. And we put the number inside, we get E. Okay, this is the one we want to improve.